So today we're very happy to have Otad Lem from MIT, who's going to be telling us about non-invertible Gauss law and axions.
Okay, thank you. So first of all, I'd like to thank for the invitation. It's really fun to be in Chicago, and I'll be here for the rest of the week. So look forward to many interesting discussion. And today I'll be telling you something about non-invertible Gauss laws and axions. So this is mostly based on this paper that I wrote with Ichi Choi and Shu and Shao from Stony Brook. And let me also bring up another paper by Yokokura that discussed similar ideas as in our paper. And it also appeared at roughly the same time as our paper. So if you're interested in the subject, definitely check out both our paper and their paper and his paper. So okay, now it works. Okay, so first of all, what are axions? So axions are, in short, periodic scalars that couple to gauge fields, and it couples to gauge fields through their instant density. So here I write down the Lagrangians for axion that couples to U1 gauge field. So here the field theta is the axion field, and it has a 2π periodicity. And it couples to the gauge field through its instant density that is given by F wedge F. Okay, so axion at the beginning was first proposed as a solution to a strong CP problem. And later it was found ubiquitously in string theory. And now it becomes a promising candidate for dark matter. And there are many, many experiments that are designed to search for axions. But today my talk will be focused less on the pheno aspects, even though at the end I will talk a little bit about applications towards quantum gravity, and hopefully that connects to some pheno aspect. But my talks will start with old stories that concerns more the formal aspect of axion-Maxwell theory. So this is related to the notion of electric charges in axion-Maxwell theory. So there was an old observations in the literature which says that there's no conserved, gauge-invariant, and quantized electric charge in axion-Maxwell theory that can be measured using an ordinary Gauss law. So one way to think about this is that we can understand this more physically through the Witten effect. So what Witten effect says is that if we have a non-trivial background of axions, and then we have a monopole somewhere, and this monopole will carry fractional charges. And the fractional charge of this monopole is given by theta over 2π. So theta is the axion field. So one obvious consequence is that if we shift theta by 2π, then the charge of the monopole will be shifted by 1. So because of this, then there's no gauge-invariant notions of electric charge. So another way to think about why there's the electric charge is not conserved is that we can think about the following process. So let's imagine that somewhere in the space-time there's an axion string sitting somewhere. So an axion string is a string. If you go around the strings, the theta field, the axion field will be winded by 2π. Okay, so now this is axion string placed in somewhere, and then we can pair create a monopole and anti-monopole pair out of the vacuum. And then we bring them around this axion strings. But when we do that, because theta winds around by 2π, and also because of the Witten effect, when we annihilate them, we will left behind an electric charge. So that's why there's no conserved gauge-invariant quantized electric charge in an axion-Maxwell theory. So Witten effect gives us a physical way to understand that. And in fact, this phenomena, that I mentioned that the subtlety of electric charges is a rather general phenomenon. And this exists whenever there are a billion Simons type terms that are present. So in the talk, I will be mostly focused on axion-Maxwell theory. But the story also generalized straightforwardly to the case of supergravity. So, and we'll see how it goes. Okay, so let me first give you the main takeaway of today's talk. So this is about non-invertible Gauss law. So I'm going to show that in axion-Maxwell theory, an ordinary Gauss law is naturally replaced by a non-invertible Gauss law. And this non-invertible Gauss law is closely related to a symmetry, and which we call it non-invertible one-form symmetries. And I'm going to explain what I mean by non-invertible one-form symmetry. And just like ordinary symmetry, this non-invertible one-form symmetry can impose selection rules on correlation functions. So for example, the selection rule that imposes on correlation functions, we will see that it's closely related to the Witten effect that I discussed before. And also this non-invertible one-form symmetry gives us a global symmetry way to understand some cosmic result discussed in this paper by Kellen and Harvey, and also by Nuglish on anomaly flows. And also towards the end of the talk, I'll discuss some implications of this non-invertible one-form symmetry in quantum gravity, and hopefully that will connect to some final aspects of axions. Okay, so is there any question at this moment? So this is basically the summary of today's talk.
Is there a connection with page charges?
Yeah, you already anticipate what I'm going to say, yeah. And I'm going to, yeah, just wait, and I'm going to talk about page charge. Okay, so now I'm going to mention some details. So let me first recall how Gauss law works. And so let's consider just an ordinary Maxwell theory. We don't know any axion field. So in this, in an ordinary U1 gauge theory, we can measure an electric charge through Gauss law. So the idea is that we have an electric particle sitting somewhere. We just find a surface that encloses this particle. Then we integrate over the electric field, and then we'll measure the charges. And what's nice about Gauss law is that this process is a topological process. So as long as you pick some surface that encloses the charge, then that's good enough. So because in the vacuum, what happens is that because in the vacuum, there's no electric current, then the electric field is divergent free. And that's why the charge is a topological charge. So if we deform it, it will give us the same answer in the vacuum background. So this is how Gauss law works in a U1 gauge theory. And it turns out we can also understand Gauss law through a symmetry way. So let's consider a limit where all of the electric particles are extremely heavy. So when particles are extremely heavy, then their wall lines will leave behind some defects in the theory. And this defect is nothing but the Wilson lines in Maxwell theory. So then the Gauss law now becomes closely related to symmetry. And this is the U1 electric one-form symmetry that people discuss. And this U1 electric one-form symmetry is generated by a topological surface operator. And this topological surface operator is nothing but the exponentiations of the electric charge. So one way to think about the actions of this symmetries or this one-form symmetries on this Wilson line is the following. So let's consider we have a Wilson line sitting somewhere. So in 4 dimensions, we can find a surface that links with this Wilson lines. So this is what I've drawn, but this is at a fixed time. So in a space-time picture, this dot really is the electric charge. This is just an instance of the Wilson lines at a fixed time. So now, because we know that this surface is topological, we can just shrink it. And when we shrink it, we'll again get back the Wilson lines, but then it will speed up a phase, and that is controlled by the charge of the Wilson lines. So in other words, the charge is related to representations of the U1 symmetry. Okay, so this is just how ordinary Gauss law works and how it is connected to one-form symmetry. And now let's.
So if sigma now is an open surface, is that reduced to some? Is integral inside is some kind of that is in this exponent is some kind of a Wilson or Tooth loop?
Oh yeah, that's right. So this will be related to a Tooth loop. But this sorry, yeah, a Tooth loop. That's right. Related to a Tooth loop, but it's an improperly quantized Tooth loop. So because this unless you alpha is 2 pi, otherwise it's improperly quantized. So here I only mentioned the electric symmetries. So it turns out that if we consider the axion-Maxwell theory with the axion field turn off, there's a zoo of symmetries that exist in the theories, and they will play important roles in the rest of the talk. So let's discuss what are the possible symmetries that appears just in this theories. So this theories consists of a free axion field and free Maxwell theories. Okay, we don't turn on the axion photon couple. So I already mentioned electric one-form symmetries, which acts on the Wilson line. So on top of that, there's a magnetic one-form symmetries, which acts on the Toph line. Other than this, there's also a symmetry. So let me also mention that a Toph line is just like Wilson line is the world line of an electric particle. A Toph line is the world line of a monopole. So other than this, there's also a shift zero-form symmetry that shifts theta by a constant. And more interestingly, there's a two-form symmetry as well. So what this two-form symmetry does is that it acts on the axion strings. So imagine that we have an axion string sitting somewhere. Then this winding two-form symmetry does is that it will measure how many times this theta winds around these axion strings. So that measures the holonomy of theta around the axion string. So this is the complete list of symmetries of this theory. So now the questions that we would like to ask is what happens if we turn on a non-trivial photon that axion photon couplings? What happens to this list of symmetries? Okay, so let's turn on the symmetry, turn on the coupling. So this is a coupling. So it's a theta F wedge F coupling. And what's interesting is that this coupling turns out to be not gauge invariant unless the coefficient K is quantized to be an integer. So a quick way to see that is that if we shift theta by 2 pi, this thing will be shifted by K times the instanton density. And we know that the instanton density is given by 2 pi times I. So this thing will only be gauge invariant if K is an integer. So axion photon coupling is quantized because of the gauge symmetry.
Why do you call it gauge invariant? So I didn't understand.
Yeah.
So you are shifting theta
By 2 pi.
yeah, but it's not related to changes, gauge changes what you are making.
Oh, but the axion is a periodic scalar, right?
I think
So-
you just meant redundancy in the.
Yeah.
Okay.
That's all I mean by redundancy. Okay, so now we will ask what happens to the various symmetries as we turn on K. So first of all, the magnetic one from symmetry and the U1 winding symmetries that are just generated by d theta and the magnetic field, and this part will remain intact. So there will still be a U1 magnetic one from symmetry and the U1 winding two from symmetry. What's more interesting is that the shift zero from symmetry, the shift theta, and then the electric one from symmetry that acts on the Wilson lines is broken. And it turns out to be broken to ZK. And I'm going to say more about this later. And what's more interesting is that if K is non-zero, K is greater than 1, then we have in total 4 symmetries. And these 4 symmetries combine into a more complicated or more sophisticated objects that's known as higher group symmetries. I won't be able to talk too much about this, but obviously you have Clay here, so he will be able to tell you more about this. Okay, so now let me discuss more about why the symmetries is broken from U1 to ZK. So the short reason is that this is because the Gauss law now becomes anomalous. So let me explain why I say the Gauss law is anomalous. So before, if we don't turn on axion couplings, we just have this, we just relate the divergence of the electric field with the charges, right? With the currents. But now, because of the axion couplings, we have this extra terms that come out of the axion couplings. So that's why I say this is an anomalous Gauss law. And let's try to understand what's the consequence of this anomalous Gauss law. So one obvious thing that happens is that the charges that we defined before will not be a good charge anymore. So before we define an electric charge by integrating the electric field through some surfaces. So that's how we define an electric charge. But this electric charge that we define will not be topological anymore if we have this non-trivial axion terms, axion coupling terms. And the reason is very simple. So let's imagine that we are in a vacuum background. So we don't have J. So we have 0 here. And then we just want to ask whether this charge is topological or not. So this charge cannot be topological because the integrand now is not a closed form. It equals to an extra term that's given by d theta and f. That's why this is not a topological charge. In that sense, the Gauss law is anomalous.
Is d theta and f is not d of theta wedge f?
D of theta wedge f. It is d theta wedge f. D theta is 1 form.
Well,
wedge was
You mean it's not exact? Yeah, it's
Not
because theta is not a well-defined expression. Because theta has jumps, it's dangerous to try to write theta wedge f in the integral.
Oh,
Of course, he'll do that momentarily, but you have to be careful when you do that. because
That's right.
it can jump.
exactly. I'm going to say more about that in the next slides. So it's related to page charge. That's okay. So it turns out we are not completely doomed. We can still define something that is topological, and this is closely related to page charge. So what's the idea? The idea is that page suggests that why don't we just introduce an extra terms in the surface integral? So this is also related to Daniel's questions. So we can write the terms before d theta times f. Try to write it as a differential of another things. So we'll write it as d times d acting on theta times f. So now this charge will be a topological charge because in a vacuum backgrounds we don't have any page current, and this integrand that appears in the surface integral becomes the closed form. So that's why this will be a topological charge. So very good. So we get a topological charge that seems to solve the problem, but not quite. So the reason why it's not quite is that this charge is topological, as we already discussed, and it turns out this charge is also the natural charge that is quantized in axion-Maxwell theory. So we achieved at least 2 of the goal, It's a topological charge, it's a quantized charge, but this is not a gauge-invariant charge. So the reason is very simple. So this is the expressions. So if we shift theta by 2 pi, we see that this charge is not invariant. It will be shifted by an integral, a surface integral of f. So that's why this is not a gauge-invariant charge. So this is the main problems with the page charge. Okay. So okay, again, there's something we can do. So even though the page charge is not gauge-invariant, the things that really interest us is the exponentiations of the page charge. So this defines the symmetry operators. So even though the page charge is not gauge-invariant, some symmetry operator can be gauge-invariant. So let's do an example. So let's consider a ZK1 from symmetry operator. So I raise this, I put this charge in the exponentiations, but with a specific coefficient given by 2 pi I over k. So this is the expression of the symmetry operator. So claim is that this operator is gauge-invariant. And before I already mentioned it's topological and conserved. So this is a good operator. So let's see why this operator is gauge-invariant. So the reason is following. So if we shift theta by 2 pi, we'll shift it by a surface integral of f times I. But we know that a magnetic flux is always quantized to be 2 pi integer. So that means that this charge, this operators will be shifted by an exponentials of 2 pi I, which is always identity. So that's why this is a gauge-invariant topological and quantized, gauge-invariant topological operator. So because of this, we see that the U1 symmetry that we started with, after adding the axion photon coupling, is broken to ZK. Okay, so this reproduces the claim that I mentioned before. So in particular, we can consider a very extreme case where we set k equals to 1. So in that case, the symmetries, the invertible symmetries will not be completely broken. So it appears to be broken. But I already gave away the main takeaway of my talk. That is, however, I'm going to argue that actually there are certain things that survive even when k equals to 1. So I'm going to show that this the electric quantum symmetry will resurrect as some more subtle objects, which I'm going to describe in the next slide. So, is there any questions at this moment? Okay, good. Then I'll move on. So in the rest of the talk, I only consider this extreme case where k equals to 1. And in this case, there's no invertible symmetry to talk about. So now let's just be less ambitious. Let's don't discuss all the one-from symmetry operator. Let's just discuss this one-from symmetry operator as some rational angle. And this rational angle is given by 2 pi p over n. So p and n are co-prime integers, okay? So this covers all the rational angles. So again, this is the operator that we want to look at. But this operator is not gauge-invariant just simply because we have this extra terms. So the reason why this is not gauge-invariant can be understood in a more simple way is that this is a fractional Chern-Simons term. So we know that Chern-Simons term will not be gauge-invariant unless the coefficient here is an integer. Because if we shift theta by 2 pi, we see that it will be shifted by fractional by fractions of 2 pi I. That's why this is not a gauge-invariant operator. So the problem now boils down to this fractional Chern-Simons term appears here, appears in the definitions of this operator. But of course, fractional Chern-Simons terms is not some monsters that we don't understand. So in condensed matter, fractional Chern-Simons terms are often used to describe the response of some systems. So for example, if we consider fractional quantum Hall states, then we can get a fractional, we usually get fractional response, and they are described by some fractional Chern-Simons term. So even though this fractional Chern-Simons terms are not gauge invariants, they can still be quite useful in physics. And of course, we know that, like for example, fractional quantum Hall states has a more precise and gauge invariant descriptions, which avoids the problems of non-gauge invariants. And this descriptions often involve some topological quantum field theories. So for example, a laughing state, which describes the fractional quantum Hall, is described by level 3 Chern-Simons Lagrangians. So similarly, we can replace this fractional Chern-Simons terms by some properly defined topological quantum field theories, which has similar response. So this topological quantum field theory is a ZNT-QFT in 1+1 dimensions. So this is the ZNT-QFT. So we have a scalar field, we couple it to a one-form field, and this defines a ZNT-QFT. And then we couple this TQFTs to the field theta and A. So we can relate these two actions in certain ways. So one way to relate this to actions is that we can imagine integrate out C. So if we integrate out C, we learn that phi is related to theta. So in particular, phi is given by minus p over theta. So if we substitute this relations back to this terms, then we reproduce the fractional transimus terms. So essentially what I'm saying is that this fractional transimus terms describe the response of this logical quantum field theory. But you see, this cannot be correct because this cannot be completely correct because I started with the actions, which is gauge invariant and well-defined, but I end up with the descriptions, which is not gauge invariant. So the only possibility is that when I integrate out C, I'm actually doing something slightly illegal. And the reason why this is illegal is the point. So when I integrate out C, I learned this relations, right? But remember that the field phi and thetas, they are compact field. So they have a redundancy of shifting them by 2 pi. But these actions will not respect this redundancy because if we shift theta by 2 pi, we learn that phi has a redundancy that is given by fractional powers. So that's why these equations or this integrating out procedure is not compatible with the compactness of phi and theta. That's why these two actions cannot be related in a trivial way. But nevertheless, we know that just from the experience with fractional quantum Hall states that we should really use topological quantum field theory to describe the systems. Okay, so now with this discussion in mind, then this motivates us to define a new surface operator, which is closely related to page chart. But now what we do is that we stack the topological quantum field theories on these surface operators. So remember that when we define the page chart, we have these expressions plus the fractional transimus term. But now we replace the fractional transimus terms more properly defined topological quantum field theories given by this. So let me emphasize that I have this field phi and C that live on the surface of sigma. And these fields don't define any asymptotic states. So in particular, we will path integrate over phi and C over this surface. So that means that they are just dummy variables that help us to write down this topological operators in a more local way. Okay. So this operator is written down as manifestly gauge invariant. And it's also topological, but we will see that the price to pay is that this operator turns out to be non-invertible. And I'm going to explain more why this is non-invertible. So a quick way to see that this operator is topological is just we can sort of reduce this topological quantum field theory back to fractional transimus terms, and this can give us a topological operator. But there's a more rigorous way to prove it, and I won't be able to explain it today. And this is related to a procedure that we define in a paper called half-hire gauging. I'm happy to talk about this after the talk if people are interested. But the basic claim is that this operator is gauge-invariant topological. So now I just need to show that this operator is non-invertible. And let's check it by explicit calculations.
How much redundancy is there in choosing the 2D TQFT that gives you that response? Like how much wiggle room do you have there?
Okay, good. It's a very good question. So there's a huge amount of redundancy, and we don't fully understand what's redundancy. So here I just pick a choice to define this operator.
Right.
Yeah, and that this operator already does most of the job. Yeah.
But does anything that you're going to tell us from now on depend on that choice or not?
Most of that will depend. Many of that will depends on the choice, but some will not depend. I can mention along the way which will depends on the choice. Yeah, but that's a good question. Okay, so now let me just explain why this operator is non-invertible. And to see that, we can just check the fusion explicitly. So if the operator were an invertible operator, what happens is that we can take an operator and then we can fuse it with its complex conjugations. So when we do that, we should just get the identity operator. But in this case, when we fuse these two operators, D and D bar, we get a very complicated objects that involve path integrating over various fields. And it's probably not hard to convince yourself that this cannot be an identity operator. So because of this, the fusion is non-invertible. So that's a hallmark of this operator. And this complicated monster actually has a nice interpretations. So this is related to the other two symmetries that I mentioned before. So it turns out that you can decompose this operator in the following way. So it can be decomposed into two sums. So the first sum is easy to understand. We essentially just sum over the magnetic quantum symmetry surfaces that wrap around this surface sigma. So this is just a sum over magnetic quantum symmetry surface. And the second sum is more interesting. The second sum turns out to be related to what has been defined in this paper and also previous paper. It's known as the condensation defect. So condensation defect, roughly speaking, can be thought of as taking the winding two-form symmetries, and then we gauge it along the surface. So we only gauge this winding two-form symmetry along the surface. So from the perspective of the symmetry operators, gauging just means that we're summing over all possible insertions of the symmetry operators. I notice that we are gauging two-form symmetries, which are generated by some topological lines on some surfaces. So that means that the surface must be a sum that involves summing over all possible insertions of lines wrapping around one cycles along this surface. So in short, we learn that by fusing D with D bar, we get the surface operator of the magnetic quantum symmetry and the surface operator of the winding two-form symmetry. Okay, so this is a non-invertible fusion.
So is this property sensitive to the choice of the TQT?
Oh, good. That's good questions. I think yes, yeah, I think it is sensitive to the choice. That's right, yeah. But there, in some sense, there's a notion of simpleness that we can impose that more or less fix this fusions. But so far, I'll just take all of my discussions to assume that I'm picking a very specific TQF.
Can you repeat what you said? A notion of what?
A simpleness. So you can define a notion of simpleness of a defect. So when I say a defect is simple, it means that it cannot be decomposed into sum over other defects. Okay, good. So now I mentioned this operators. So this operator will be topological, and the claim is that this operator will replace the notions of Gauss law in axion-Maxwell theory. And how this works is following. So let's imagine that we have a charge, a particle sitting somewhere, let's say an electron sitting somewhere with charge Q. Then we can wrap around this surface operator around this charge, and then we can shrink it because it's topological. We can shrink it and we see what we get. So it turns out that when we shrink it, it just acts like an ordinary Gauss law. So it will return back to electrons, but then it will come up with a phase, and this phase is controlled by the charge of the electrons. So again, we see that this operator can measure the electric charge of the electrons. But more interestingly, we can ask how this operator acts on monopoles. So in particular, I will consider just a basic monopole, a charge one monopole. So we again take this operator and wrap around this. Okay, so we know that the monopole will thread through, will source some magnetic flux. So because of this, it will create operators on this surface, on this like non-invertible surface operator. The reason is following. So remember that we have these terms in the definition of this non-invertible operators. And when we have monopoles that is sitting in the middle of this sphere, then this will create non-trivial magnetic fluxes on the sphere. And this magnetic flux is give us a non-trivial integral over dA. And because of this, the fluxes effectively generates a local operator that is given by exponential I phi. So the final result is that having a monopole sitting in the middle of this operator D will create an operator exponential I phi. But what's special about this operator is that since we're dealing with a Zn TQFTs on this surface, a one-point function of exponential I phi has to vanish in this Zn TQFT. So that means that when we wrap this surface operator around, we actually get 0 out of it. So this means that the surface operator annihilates the atoll lines or annihilates the monopoles. So because of this, we say this is a non-invertible Gauss law because it annihilates some defects or some particles. Is there any questions at this point?
It is a similar phenomenon to the absence of electric charge of monopole when there's a massless charged particle.
Massless charged particle. Are you having in mind like fermions or?
Massless fermion.
Massless fermion. But can you say the question again? Sorry.
So as you know, when this Witten effect to give the electric charge to monopole vanishes when there is a massless fermion, massless charge fermion. So I was wondering if this is some similar, analogous effect.
Not exactly the same, because in your case, it's because chiral anomalies of the, or you can say there's an extra little more trap on the monopoles. But here it's just because, actually, I'm going to mention a little bit more why this analysis. So the reason is because monopole charge is not well defined, because monopole charge is given by theta over 2 pi, and then theta has a redundancy of shifting it by 2 pi. So that means that this monopole charge has ambiguity. Yeah, I'm going to mention more in the next slide.
Maybe it's also worth emphasizing, this is the exponentiated charge generator that's giving you 0, not the charge itself.
Oh, I see.
So it's like, it's a much weirder equation. E to the Q equals 0.
That's right. Yeah.
I see.
So this operator is not a unitary operator. Thanks. Okay, so it's actually related also to your questions that now we can ask a more refined questions. Let's ask how does the operator act on a charge M monopole? And then we can ask what happens. So as before, because we have a monopole sitting in the middle.
The Q on the subscript there, M comma Q.
Oh yeah, good. I'm going to mention this. Yeah. So this is a charge M monopoles, and then this will create a magnetic flux again on the surface. And this magnetic flux will again create a local operator on this surface. And this local operator is given by exponential I M phi. So M is the magnetic flux. So now something interesting can happen. So in a ZN TQFTs, a 1-point function of exponential I M phi depends on whether M is divisible by N or not. If M is not divisible by N big N, then this 1-point function has to vanish. So that means that when M is not divisible by N, we again see that this operator annihilates the magnetic monopole. On the other hand, if this little m is divisible by big N, then we learn that this 1-point function doesn't vanish, and this operator will act on the monopoles just like an ordinary Gauss laws. It will measure its electric charge. So this little q is essentially the electric charge label of a monopole, which comes in this phase. And let me give more intuitions about this charge, little q. So what this Gauss law is telling us is that the electric charge of a charge M monopole, there's certain notion of electric charge of charge M monopole one can define. And it turns out is that this electric charge is well-defined modular little m. So if your magnetic charge, let's say, has a charge 2, has magnetic charge 2, then we can distinguish 2 different monopoles. One carries no charge and one carries 1 charge. But we cannot distinguish the monopole that carries charge 0 and the monopole carries charge 2. So that's the content of this Gauss law. And the reason behind this is because of Witten effect. So you see that a monopole, a charge M monopole has electric charge that is given by little m times theta over 2 pi. So if you shift theta by 2 pi, the electric charge of a charge M monopole is shifted by little m. So that means that the charge has an ambiguity of little m. And that's why only the charge modular little m is well defined. Okay. So this Witten effect can also be understood as a consequence of anomalous flow. So let's consider a flowing process. Let's consider that we have a top line sitting somewhere in the space-time. Okay, so then around the top line, the surface that wrap around the top line will have non-trivial magnetic flux. Then we can ask what happens if we do a dimensional reductions of this axion-photon coupling. So the axion-photon couplings will reduce to this expressions. So this is because we're just integrating little f over the spheres will give us little m that's rid of the magnetic flux. So this tells us that the axion-photon couplings give us a term that is given by theta times f with the coefficient little m. And this term is defined in sort of like a half space, which terminates at the top line. Okay, so this is what we get from axion-photon coupling. But what's interesting is that this term is actually not well defined. This term is actually not well defined in the if this ends at some near top line, because if we shift theta by 2 pi, this term will give us an integral, will give us a Wilson line, insertion of Wilson lines, a charge M Wilson lines on the top lines. So this is essentially the content of anomaly flow. That is the actions in the bulk, it's not gauge, it's gauge invariant if it's on closed manifold, but it's not gauge invariant on open manifolds. And you need to add some things on the boundary to compensate it, make it gauge invariant. So from the perspective of the top lines, this can be understood as a mixed anomaly, but it's an interesting mixed anomaly. It's a mixed anomaly between the S1 parameter, theta, and the U1 gauge group. And what this mixed anomaly is saying is that if we shift theta by 2 pi, we'll get a charge M Wilson lines on this atoll lines. So this just means that the electric charge of the atoll line is not well defined up to a little n. This reproduces the Witten effect from an anomaly inflow perspective. Yeah. So it turns out this anomaly inflow picture also applies to axion strings. So let's consider an axion strings sitting somewhere. And so what's special about axion string is that if you go around axion strings, theta will be winding by 2 pi. And again, the axion photon coupling will reduce to some terms that is given by the Trin-Simons term of big A, of the U1 gauge fields. And a Trin-Simons term is not well defined on open manifold. That's why on the axion strings, there must be electrically charged states that cancel the anomaly. And this is again reflected in the non-invertible Gauss law. But now we are dealing with something more interesting. So we're dealing with a string. We're not dealing with a particle. So the way to define this non-invertible Gauss law is the following. So first of all, if you have a strings, we can take an S1 that wrap around the strings. Okay, then we can extend, we can place a surface, we can define a cylinder by extending this S1 along the direction of the strings. And this will define a surface, and then we can place our operator D on the surface and ask what happens. So again, this will depends on whether the string, whether the winding of the string W is divisible by big N or not. If it's divisible by big N, then this will live behind U1 symmetry lines. If it is not divisible by big N, this will annihilate this again. So this again reflects the anomalies that I mentioned before. So we see that the anomaly is closely related to anomaly inflow is closely related to the actions of non-invertibles. Now I'm going to make a lip. I'm going to argue that this non-invertible topological surface operator that we constructed before find a non-invertible one-form global symmetry. I want to call them a symmetry. So that's really the conceptual lip that I would like to make. And then the obvious question is that why is this a valid terminology for this surface operator? So there are many good reasons. So one reason is that I'm going to show in the next slides that this symmetries, this surface operator actually impose selection rules. They also impose certain conservation laws. So that's why they are qualified as a symmetry. The second reason is less understood, but it's better understood in 1+1 dimension, is that sometimes this topological, non-invertible topological operators can also be gauged, just like an ordinary symmetry. And the more interesting things about this non-invertible operator is that they are invariant under renormalization flow. And the reason why they are invariant is very simple, is that when we do renormalizations, we're changing the scales. But because these operators are topologicals, they will survive at every scales. That's why they are invariants under renormalizations. And because of this, we can use it to constrain renormalization proof flows, and it has been done in many different contexts. Okay. So now I'm going to talk about the selection rules imposed by this non-invertible one-form symmetry. And before doing that, we need to understand how this non-invertible symmetry acts on the various things. So when I say how it acts, what I want to consider is the following process: that let's say we insert some defect somewhere, and then we have the topological operator placed somewhere. And then we can sweep this topological operator past this defects and see what we get. So for example, if we sweep this operator past the Wilson lines we get a place, this is expected from the actions of the Gauss law. What's more interesting is how this topological surface operator acts on monopoles axion strings. So it turns out that we call the actions as a non-invertible actions in the following sense. So for example, if we bring this operator, this topological operator past the toph lines, we see that it will stretch out a topological line that stretch between the toph lines and the surface operators. So what happens is that it maps a line operators to a line operators that are attached with some topological lines. So in that sense, it's a map that is non-invertible. Is that it doesn't map the operator with the same dimensionalities to the other operator with the same dimensionality. Instead, this is attached with something. So similarly, if we strip this topological surface past the axion strings, we'll stretch out the topological surface out of it. So this topological lines and topological surface has a very nice interpretations. So for example, this topological lines turns out to be related to the winding two-point symmetry. And in fact, this is a topological line that generates the winding two-point symmetries. And this will be crucial in our discussion of selection rules. So as I mentioned that this non-invertible one-to-one symmetry imposes selection rules and correlation functions. And it turns out that these selection rules are closely related to the Witten effect. So at the beginning, I already mentioned that there's a process one can imagine is that we have an axion string sitting somewhere, and then we can pair create a monopole anti-monopole, and now then annihilate them and get electric charge. But now we can rephrase this process. So this is a physical process into the language of correlation functions. So let's consider a limit where all the dynamical objects, the electric particles, monopoles, and the strings are extremely massive. And that's what we learned. So in that case, we learn the following. So we can imagine that we insert an axion string somewhere, and then its world sheet will define a surface operator in space-time. Okay, so a surface operator can link naturally with a loop in 4 dimensions. And so we can imagine that we have a toe line that link with our surface defects, which correspond to axion string. And the meaning of this toe loop is the following: is that this is essentially the creation of monopole and anti-monopole pairs, and we bring them around the axion strings. So that's what we are doing with this toe line that wrap around the axion string world sheet. But because of Witten effect, what we learned is that the correlation function has to vanish unless there's a Wilson line that is speed up from this toe lines. So that means that the correlation function is non-trivial only if there's a Wilson line that with a very specific charge that is given by m times w coming out from this toe line. And we're going to see how this can be reproduced using selection rules. So specifically, we'll consider the following correlation functions. So we have axion strings, which is a surface defects, which links with a line defects, which is a toe line. And the axion string has charge W, and the toe line has charge N. And then we allow ourselves to attach some Wilson lines, Q1 and Q2, to the toe line and the axion string respectively. And we want to ask, in what case is this correlation function not trivial? So one way to derive selection rule is the following: is that we just introduce this little non-invertible operator sitting somewhere, and we let it wrap around the WQ1 and see what happens. So if we wrap it around the WQ1, then we can shrink it. And when we shrink it, it will pick up a phase, and the phase is given by Q1. And then with a coefficient P over N that is determined by the label of this non-invertible symmetry. So we get a phase out of it. So another process we can imagine is that we can make this loop large, and then we shrink it somewhere here. Okay. So if we do that, again, we will pick up a phase, but this phase will be related to the charge of Q2. So now we get an equality between these two, and their prefactor is the same prefactors. So that means that this correlation functions will be non-trivial only if this phase are always compatible with each other. And notice that this phase are defined for every V and N data coprime. So that means that these two phases are equivalent to each other only if little q1 is the same as little q2. So it tells us that if we have a Wilson line that come out of the toe lines, then there must be a Wilson line that comes in to the axion strings. Okay, so this is not related to Witten effect yet. Now we are going to relate it to Witten effect.
But how did you know that, like, so the HMSW linking was not like that correlation function doesn't vanish, right? So you use like AX is equal to BX, therefore A equals B. I guess you have somehow assumed that that thing is non-trivial.
Oh, you mean this thing?
Yeah.
Oh, no, so I want to say that So first of all, we know that these two has to be equal, the same as each other.
Yeah.
So if the phase is not compatible with each other, the only way these two can be the same is that this has to vanish, right?
Yeah.
So that tells us the selection rules.
Oh, I see. Okay.
Yeah, okay. Okay, now I'm going to do something more interesting. Okay. So what I'm going to do is that instead of shrinking this operator directly here or here, we'll bring it past the Atof line. So remember that when we sweep this operator little d, big D past the Atof line, we'll create some topological lines that are related to winding symmetries that is attached to the Atof line and also to the topological operators. So when we bring it past, we stretch out some topological lines. And now we can shrink the operator. Okay, so now we are left behind a Atof line that is attached, topological line that is related to winding charge that is attached to the Atof line. Okay, so now we can do the following things. We can bring this endpoint around, and then we can shrink this line again. But when we bring this point around, this topological lines will link down trivially with the axion string worksheet. And because this thing is the winding operators, so this will measure how many times an axion field winds around the axion strings. So now if we do this, so this is the things that I'm doing. I'm bringing the endpoints around, then I'll get out a phase. This phase measures how many times the axion string winds. And it also have a coefficient related to the monopole charge. And this is because when I bring this operator past, the Atof line that stretch out is related to little n. So I get a phase that is given by n times W. Okay. So the next things I can do is that I can just make the lines that is attached to a Atof line disappear and just bring it out and then shrink it. So the final thing that's left behind is that we get the same correlation function as before, but with a different phase. This phase is controlled by little n times little w. And again, these two things are compatible with each other only with Q1 is the same as m times w.
Sorry, can you repeat the first operation?
The first, which operation?
Go before. How did you get this guy?
Oh, so this is the things that I mentioned before, that if you sweep past the topological operator across the Atof line, you will stretch behind some topological lines. Okay. And this is the topological line. So yeah. So essentially we learned that the correlation function is not trivial only if Q1 is the same as Q2 and it's the same as m times W. This is the Witten effect that we discussed before. So here we see that selection will reproduce the Witten effect. And it comes from the interesting non-invertible actions of the surface operator on the Atof and the axion string motion. Okay. So I'm going to move on. Oh, actually, is there any question at this moment? Okay, good. Then I'll move on to talk about applications now. So it's really, I'll talk about applications in quantum gravity and hopefully to connect it to some field aspect. Okay, so the story starts with two pieces of lore that people often discuss on the quantum gravity. So the first piece of lore is the no global symmetry conjectures. That is, there's no global symmetry in quantum gravity.
Did you sweep like the extra factors that come out if you like pop a bubble?
Sorry, can you say? Oh, sorry. Are you saying that if I shrink this, there's a bubble?
Well, even before that, like when you brought it through the blue.
Oh, you mean this one, right?
Yeah.
Yeah. So when I shrink it, I don't get an extra. Are you worried about the normalizations or?
Yeah, like usually when there's like the quantum dimension of the.
Yeah, that's a very good question. Yeah, actually, that's a very, very good question. So in the slides before, I had a little footnote here, which says that I'm working with a surface operator. Okay, the surface operator you can normalize it by adding some counter terms, and that is related to the Euler characteristics. So you can always normalize operators such that it has a quantum dimension 1 on a sphere. Does that make sense?
Yeah.
Yeah. So this is specific to operators that has an even dimension, so you can add Euler characteristic to make it normalized, properly normalized. No, but that's a very good question. Good. So let me go back to quantum gravity now. So I mentioned no global symmetry conjectures. There's also another conjecture that is related to completeness of the spectrums. What it says is that if your quantum gravity has some gauge fields, then the spectrum of gauge charges has to be complete. That's every representation of the gauge group has to appear in the spectrum. Okay. So it turns out that these two statements are not completely unrelated, and they are related thanks to the recent developments of generalized global symmetry. And I'm going to demonstrate this in one example. This is an example of U1 gauge theory. So I don't have any axion field. I just talk about U1 gauge theory. So in this case, if we have a complete spectrums of gauge charges, then that means that the Wilson lines can end somewhere. It can end and or terminate at some charge field. Okay, so this is what I've drawn here. A Wilson line terminates at some field. So this then implies that the U1 electric quantum symmetry has to be broken. It has to be completely broken. The reason is very simple. So let's assume that this symmetry is not broken. Then we will have some operators, a surface operators that is topological. So let's wrap this surface operator somewhere around here. So there are two possible things we can do. One is that we can shrink the operators, then we get an non-trivial phase, the readout of the electric charge of the Wilson lines. Or we can just bring this operator past the termination point, and then we'll shrink it again. And this will not create any phase. So this, but we know that in this theories, Wilson lines terminate at charge fields as non-trivial correlation functions. So this tells us that we get a contradictions. So this means that the U1 electrical quantum symmetry has to be broken. So the assumption that we made at the beginning must be wrong. So in short, is that we have a complete spectrum. A complete spectrum means that Wilson lines can end, and the endable Wilson line means that the electric quantum symmetry has to be broken. So that's a channel of logic. So this is a very nice way to relate completeness hypothesis with no global symmetry conjectures. And this global symmetry is related to the electric quantum symmetry that feature in U1 gauge theory.
So from the no global symmetry conjecture, you can deduce the completeness hypothesis. But which direction?
Yeah. So far, yeah, that's a very good question. So far, I'm only talking about completeness spectrums implies no global symmetry conjectures. If we have a complete spectrum, the symmetry has to be broken. Yeah, but one can ask, why the lack of electric quantum symmetry implies completeness hypothesis? This is because the only way to break, I should say, I think I can say the only way to break the electric quantum symmetry U1 gauge theory, just U1 gauge theory, is by adding charge fields. So that means that if the electric quantum symmetry is broken, it can only be broken while having a complete spectrums. So you're right. So far, I'm only talking about completeness spectrums implies electric quantum symmetry, but the other way is also true. However, this nice equivalence between the two breaks down to more general gauge theories, and it has been noticed, and it breaks down in many places. So, for example, if the gauge group is disconnected, then this equivalence is broken down. If the gauge group is a finite non-Witten group, it's also broken down. But there's an interesting thought that has been put forward by two papers that suggest that what if we include non-invertible global symmetries into discussions? Is it possible to rescue this equivalence? So it turns out the answer is yes. So specifically in these two type of theories, it was proven that a complete spectrum is completely equivalent to the absence of invertible and non-invertible symmetries. So it's true both ways. So complete spectrums will break the invertible and non-invertible symmetries, and the lack of invertible and non-invertible symmetries also implies complete spectrum. So it turns out this story also appears in axion-Maxwell theory. So similar phenomenon also appears in axion-Maxwell theory that the lack of invertible global symmetry and the completeness hypothesis is not equivalent. So one way to see that is very simple, is that let's consider the case where k equals to 1, which is the case that I started with. So when k equals to 1, all of the electric quantum symmetry are completely broken. But it doesn't need to have a complete spectrum of gauge charges. So in that case, we learned that the lack of global symmetry doesn't imply complete spectrums. But now we can use the same logic and ask what happens if we introduce non-invertible quantum symmetry that we constructed before into considerations. So it turns out that if we do that, again, we solve the problem. So just by the same reason as before, if we have a complete spectrum of gauge charges, then the Wilson lines will be endable. And because the Wilson lines are endable, and because this non-invertible quantum symmetry acts on the Wilson lines, then this symmetry has to be broken. Okay? So this means that completeness hypothesis does imply the lack of non-invertible one-form symmetry operation. But one can ask, what happens if we break the non-invertible one-form symmetry? Does it always implies completeness hypothesis? But it turns out that it's slightly more subtle because it's true that we can break the symmetries by a complete spectrum of gauge charges, but there are more subtle ways to break it. So remember that my symmetry acts on also taut lines or acts on monopoles and axion strings. So that means that if I have a dynamical monopoles or dynamical axion strings, again, I can break the symmetries. But what's interesting is that because of anomaly flow, if we have dynamical monopoles and dynamical axion strings, they will trap some charge spectrums. So because of this monopoles and axion strings will effectively behave as a complete spectrum of gauge charges. So again, we see that just by introducing monopoles or axion strings, we obtain a complete spectrums. So that means that the lack of invertible and non-invertible global symmetries is equivalent to completeness hypothesis in the axion-Maxwell theory. So again, we save the equivalence relations using our non-invertible global symmetry.
The point is that the thin string world tube is the same as an electrically charged
Correct, yeah.
particle.
Yeah, that's right. We have a very tiny strings and then it will behave like a particle. Okay, so motivated by the global symmetry conjectures, I'm going to discuss some constraints on emergent symmetries. I think I only have 5 minutes, so I'll be rather fast. So let's now consider a renormalization group flow that ends on the axion-Maxwell theory. Okay. So, and because we believe there's no global symmetries in quantum gravities, and that means that all of the symmetry in axion-Maxwell theory, if it's embedded in a quantum gravity, there should be an emergent symmetry. So that means that various symmetries should be broken in U. So in this case, then we can define energy scales for the symmetries. So below, for every symmetries, we can define energy emergent scales. So below that energy scales, the symmetry emerges, and above the scales, the symmetry is broken. And then one way to think about how this energy scale is the following. So below the scales, the symmetry is there, and the symmetries will act on some defects that is charged under the emergence. But above the scales, these defects will become the world lines of some new degrees of freedoms that kick in. And then because this world volumes can end, and because of this, the emergent symmetry has to be broken above that energy scales. So then we can associate the various energy scales with some physical meanings. So for example, if an electric symmetry is broken, by one way to think about the energy scale where the electric symmetry is emergent is a scale where the lightest electric charge is the mass of the electric particle. Similarly, the energy scale associated to magnetic symmetry is related to the mass of the lightest magnetic monopoles. And because the winding symmetry acts on axion strings, then this should be closely related to the axion string tension. But notice that axion string tension has a different dimensionality. So it has math dimension 2. So to relate them, we have to put in a square root here. So the energy where the winding symmetry is emergent is related to the square root of the axion string tension. So this gives the physical meaning to various energy scales. Now let's see what we can learn from our non-invertible symmetry. So the key behind this is that remember that this non-invertible symmetry, when we fuse them, they fuse in a non-invertible way. And in particular, when we fuse them, it will give us magnetic one-form symmetry and winding two-form symmetries. So the fusion of non-invertible electric one-form symmetry contains magnetic one-form and winding two-form. And because of this, we learned that this symmetry cannot exist without the presence of both symmetries. So if either symmetry, either magnetic one-form or the winding two-form symmetry are broken, then the non-invertible symmetry has to be broken. So this immediately gives us inequalities of energy breaking scales. That means that the energy where electric one-form symmetry emerges must be less than the energy where the magnetic symmetry emerges and the energy where the winding symmetry emerges. Okay. And this inequality actually have a very nice way to think about this using anomaly flow. So this is because monopoles and axion strings support electrically charged states. So that means that once we have monopoles or axion strings present in our spectrums, then they will always introduce some electric charged particles. So that means that the lightest electric particle must always be lighter than the scale controlled by the monopole and axion strings. So here we see that anomaly flow gives a physical interpretation to this inequality. Okay. So I think I'm almost out of time. So I'll be rather quick about this. So it turns out this inequality that I just described has a nice applications to also weak gravity conjectures. But this is yet another conjectures related to quantum gravity. So this inequality implies a mixing of weak gravity conjectures in axion-Maxwell theories that has been observed in these two papers. And let me just be quick about what a weak gravity conjecture means. So I will state it in a more general case. I'll consider it a P-form gauge theory. So what weak gravity conjecture says is that in a consistent theory of quantum gravity, there must exist a P-1 brane whose tension must be less than EP times M Planck. So EP is the coupling of the P-form gauge theory, and M Planck is the Planck mass. So it tells us that there must be something that is light enough to break the symmetry, and its lightness is controlled by the M Planck and the coupling of the P-form gauge fields. So the statement of the mixing of weak gravity conjecture is that in axion-Maxwell theory, we will see that weak gravity conjecture for axion and strings actually implies a weak gravity conjecture of particles. So in some sense, there are some relations between different weak gravity conjectures. And this sort of gives us a consistency check of weak gravity conjectures. Let's see how this works. So first of all, if we we can talk about weak gravity conjecture for axions. So axions coupled to instantons. So instanton can be thought of as a -1 brane. So that is the case where we set P equals to 0. So in that case, the tension is can be sort of interpreted as the string instanton actions. And then the coupling is given by 1/f. F is the axion decay constant that I've written before. So then from this, we learned that the axion decay constants has to be less than E squared times M Planck. E is the coupling of the electric field. And another inequality that we can obtain is from axion strings. So now we can talk about what happens to axion strings. So axion strings is strings. So it's the case, it is specialized to the case where P equals to 2. So one way to think about this is that we can take the axion-Maxwell theory, we can dualize the axion fields. When we dualize the axion fields in 4 dimensions, we'll obtain the 2-form gauge fields. And the coupling of the axion fields is given by little f. So from this, the weak gravity conjectures give us this inequality that the tension has to be less than F times M Planck. Okay, so now combine all these things with an inequality that we obtain, we can derive the weak gravity conjectures for particles. So let's see how this works. So the first inequality comes from the inequality that we derived before, that the mass of the electric particle should be less than the square root of the string tension, of the axion string tension. And now we can use the weak gravity conjecture for axion string tensions to relate square root of string tensions to square root of F times M Planck. The next thing is that we use axion weak gravity conjectures. Then we learn that the mass of the mass of the electric particles should be less than E times M Planck. And this is nothing but the statement of weak gravity conjectures. So in short, we learned that weak gravity conjectures for axions and axion strings implies the standard weak gravity conjectures in axion-Maxwell theory. So in this way, we see that how symmetries help us to sort of unify or relate different weak gravity conjectures. Okay, so this will be very, very brief. So other than the one-form symmetries, there's also a non-invertible zero-form symmetry. And this is closely related to shift symmetries. And in fact, this is how all this discussion started. So the non-invertible shift symmetry has an anomalous conservations that is related to ABJ anomalies. And and by the same reasonings, we can obtain the energy inequalities. This tells us that the axion potentials must be less than the mass of the magnetic monopole. And there's a physical way to understand that is that before we get to monopole scales, already monopoles will be running in virtual loops, and this will create an axion potentials. That's why the energy scales of the axion potentials is less than the mass of the magnetic monopole. Okay, so in the end, from a more formal perspective, we'll see that all these invertible and non-invertible symmetries combine into more complicated objects, which is under active investigations now. That is, the more proper mathematical language to describe the symmetries is higher category theories. And this higher category theories generalize the higher groups symmetries that discussed by Daniel and Clay and many other. Okay, so let me just conclude. I think -5 minutes now. So in axion-Maxwell theories, we talk about non-invertible zero-form symmetry and one-form symmetries. And they comes from the naive shear symmetry and the electric symmetries. And we construct them by putting some topological quantum field theories on symmetry operators. And in the case of non-invertible symmetry, we learned that it acts invertibly on Wilson lines, but non-invertibly on the open axion strings. And because of this, it imposed a Witten effect. Imposed selection rules that are related to Witten effect. You also see constraints of the symmetries on renormalization group flows. And also it has various implications to quantum gravities, like Completeness Hypothesis, non-global symmetry conjectures, and weak gravity conjecture. Okay, so that's everything I want to say. I'll just end my talk with this timeline of developments on non-zero space. Thank you. Oh, go ahead.
So you promised to talk about some phenomenology.
Yeah, and the best I can only say is this. It's probably useless that axion potential is less than the monopole max. Yeah.
So maybe I can. So far, I think the result you have presented. I mean, it's very nice to
Yeah,
use
that's
the
right.
higher form or zero form non-invertible symmetry to organize the have a view. This is very interesting. And then, is there any results that previously not known that?
Yeah, that's a good sense. At this moment, not really. So everything that we say can be also understood from a more from different perspectives, by using anomaly flows and using like various calculations.
Right.
So symmetry sort of gives us a shortcut or a similar easy way to organize.
I mean, it's still very interesting, but I'm
Yeah.
just wondering, curiosity, is there any leads to some new result?
Yeah, sorry, at this moment, not quite. Yeah, not quite. Yeah. That's something we're trying to think about more. Yeah. But yeah, that's a good question. And that's also something that's really like bugs me, and I'm hoping to say more.
There was an ambiguity in your charge, and then I don't think you mentioned which statements you made depend on the choice of ambiguity. Could you maybe?
Depends on the choice of ambiguity.
So that's 2D TQFT.
Oh, you mean, that's, sorry, I forgot to mention that. So let's see. So for example, the actions of non-invertible symmetries on the Wilson lines depends on that. So the selection rule wouldn't depend on that. Actually, let me say something else. So selection rule might depend on that. So you might get weaker selection rules, but I like to claim that the selection rule that we derive here is strong enough. So for example, if you place a different kind of PQFT, you may get a weaker selection rule that maybe you learn that this two has to be the same modular or something instead of getting actually equality. That's possible. So selection rule, you might get a weaker selection rule, and you will also.
So your claim is that you're grateful to the strongest selection rule?
I don't have a proof yet, but I sort of believe that the one that we have give us the complete selection rules. Yeah, but I don't have a proof.
Because you can reproduce the Witten effect. Is that
Correct. Yeah, that's correct. Yeah.
Can you say more on why you called that the Witten effect?
Oh, actually, I should say this is a consequence of Witten effect, maybe. So Witten effect tells you that the theta will be shifted by 2 pi. Oh, sorry, the monopole charge will be shifted by 1 if theta is shifted by 2 pi, right? And then this tells us that this correlation functions has to vanish unless this equality holds. So this is really a consequence of Witten effect. Yeah. Does it make sense?
So what should I think now of Witten's original statement? Does a monopole have a theta over 2 pi electric charge if I go measure it, or is there?
That's a very good question. So it's actually related to the various charges that I talked about.
Yes.
So we can ask what is the charge that Witten used in these definitions.
Good.
So the charge he uses is not the page charge. Page charge is always quantized. So the charge we use is actually the first charge that I talked about, which is not topological. So let me go back.
No, but in Witten's case, the axion was not dynamic.
There's no.
That's correct. Yeah, that's correct.
So then you can just use this Q, right?
That's correct. That's also true. That's right. Yeah. But then that's why you can get fractional charge. So if you want to, you can also choose a different way. Just like Witten can also pick the page charge too. And pay charge will give you a properly quantized charge. Yeah. That's all. Yeah, a good way to see is you see this term. What is this term doing? This term is essentially telling you that monopole has it's canceling the fractional charge of the monopole given by theta. Yeah, so that's what this term is. Yes, there's no more questions?
Yes, let's thank the whole dot again.
Yeah.
Where are all these charge particles? Where are all these charge particles?